Welcome back, everyone. I'm really thrilled you're here for today's explainer because we are jumping straight into a massive, highly complex engineering puzzle in modern dual-motor EVs. We're talking about a critical fault code, natively known as E4, or Single Motor Degradation Mode invalid. Basically, we're looking at exactly what goes down when the very system designed to save your life actually fails. Okay, let's dive right into this. You know, modern dual-motor EVs are absolute marvels of engineering, right? They're packed with these incredible backup systems, but the stakes get unbelievably high when we ask, what actually happens when that built-in, ultimate safety net critically fails while you're cruising at highway speeds? Just consider this stark contrast for a second. Normally, you have what engineers call limp-home mode. If one motor kicks the bucket, the car safely shifts power over to the healthy motor, and you just calmly pull over into the emergency lane. Easy, right? But with an E4 failure, that transition process completely breaks down. And the reality? It's severe. You're looking at a total catastrophic loss of propulsion, or even worse, a really violent, unintended wheel lockup. So we're going to dissect this whole thing like a forensic autopsy. We'll look at how the backup plan fails, the 4 dimensions of that failure, the 60-millisecond defense, bulletproof design, and finally, the ultimate stress test. All right, part 1. The backup plan fails and limp-home mode totally collapses. So limp-home mode, or Single Motor Degradation Mode, is built on an ASIL D fail operational safety architecture. That's literally the highest standard of automotive safety risk management out there. In plain English, if your generator motor suffers a fatal hardware failure, the system is supposed to seamlessly isolate it and let the healthy traction motor take over propulsion. Simple enough, right? But when you get that E4 Single Motor Degradation Mode invalid fault, it means this exact safety net has collapsed, usually because of a massive shared software or hardware shock. Which brings us to part 2, the 4 dimensions of failure. Time for the forensic autopsy. Now, what's really wild about this is that these 4 suspects, electrical, mechanical, software, and algorithmic, they don't just happen one by one. In a highly integrated dual-motor controller, a failure in a single motor can trigger a cascading collapse across all 4 of these dimensions simultaneously. It's like a chain reaction that effectively takes down the healthy motor right alongside the broken one. Let's break down that first suspect. Okay, the first dimension is electrical. Just imagine a metallic short circuit happening in the failing motor. This creates some extreme current spikes. We're talking greater than 5 kiloamps per microsecond. That's a massive surge. And it injects this huge wave of electrical interference straight into the shared low-voltage power rails, creating an electrical tsunami that engineers literally call ground bounce. This tsunami just washes over the healthy motor's sampling channels, entirely tricking it into thinking it's experiencing a massive overcurrent. So what does the healthy motor do? It panics and shuts itself down. Then we have the mechanical and thermal dimension. Greater than 70 Newton meters. That is a massive amount of parasitic electromagnetic drag torque. It happens because the healthy motor is suddenly forced to physically drag the dead, short-circuited motor through the vehicle's gears. This uncontrolled generation creates so much drag, it can literally stall the vehicle. Plus, the friction heat from this, it can melt the motor's internal copper wires in a matter of seconds. Literally seconds. Next up is the software side of things. These systems run on multi-core processors, right? So you've got Core 0 for one motor, Core 1 for the other, and Core 2 just managing safety. When an emergency transition kicks off, there is a massive internal traffic jam of data. And if the software isn't using what are called atomic operations, you get parallel reading and writing conflicts. This causes data tearing. Basically, the cores end up reading incomplete instructions, causing fatal task deadlocks. The whole processor just crashes right when you need it the absolute most. And finally, the algorithmic dimension. See, if a physical sensor breaks, the car falls back on pure math, a sensorless observer. But remember that extreme heat from the failure? When it soars past 130 degrees Celsius, it literally doubles the physical electrical resistance in the motor. This extreme thermal drift completely ruins the math. The algorithm's calculation drifts by more than 45 degrees. This destroys the control vectors, causes incredibly violent shuddering, and just leads to a total catastrophic collapse of the backup control. So, how do engineers fight back? Part 3, the 60-millisecond defense. It is a literal race against time. 60 milliseconds. That is the absolute maximum fault-tolerant time interval, or FTTI. Think about that for a second. In less time than it takes you to blink, the vehicle's computer has to detect the failure, physically isolate the broken motor, and mathematically reconstruct a healthy state. If it takes, say, 61 milliseconds, the whole system fails. Game over. So the really crucial point here is how on earth they achieve this speed safely. Well, they use a doer-checker architecture. One core does the math, and a secondary core double-checks it in under 100 microseconds. And if it spots any corruption, it does not wait around for the software to fix itself. No way. A smart external hardware chip physically bypasses the corrupted software and forcefully cuts the gate power to the failing motor in under 1 millisecond. It is a hard, physical shutoff. But once it's isolated, the healthy motor still has to take over without violently jerking the car, right? The elegant math behind making this smooth is called S-curve smoothing. Over a tiny 3 to 5 millisecond window, the system seamlessly hands over control, limiting the torque shock to less than 5 Newton meters. This makes sure the wheels don't look up, and it smoothly caps the speed at 40 kilometers per hour, just so the driver can safely coast into the emergency lane.
All right, part 4, bulletproof design and assembly. How we actually prevent this stuff.
Preventing this is all about extreme physical tolerances. Engineers use dual isolated power supplies to keep voltage variance below 0.2%, which stops that electrical tsunami we talked about earlier. They use hardware semaphores to physically lock down data during multi-core processing to prevent that data tearing. They even install these heavy-duty strain relief brackets so intense vibrations cause less than 1 micrometer of wire slip. And over in manufacturing, every single board goes through 3D X-ray scanning to ensure soldering voids stay strictly below 5%. It's all about creating physical boundaries to protect the electrical logic. And this next part brilliantly illustrates one of my absolute favorite engineering tricks, the active search coil. Remember that algorithmic thermal drift that ruined all the math? Well, engineers realized they could actively disconnect the broken motor's windings, just leave them floating, and then use them as a pure physical sensor to read the back electromotive force. They literally turned a broken component into a perfect sensor that completely ignores temperature drift. I mean, that is just brilliant. Finally, part 5, the ultimate stress test, getting through DVPNR validation. Surviving these validation tests is absolutely mandatory before any of this hits production. They subject these units to 1,000 hours of brutal 10 to 2,000 hertz vibrations and thermal shock, just to ensure the electrical contact resistance barely even changes. They blast the electronics with extreme radiation and high-voltage injections, demanding that the signal-to-noise ratio stays incredibly strong. And on the hardware-in-the-loop test benches, they intentionally inject massive faults at full speed. They demand the system still reacts perfectly within that 60-millisecond window. Which brings us to this really powerful quote from the source material. To guarantee absolute functional safety, we don't just engineer for the expected. We engineer precise 60-millisecond mechanical reflexes to survive the impossible. I think that perfectly captures the deep engineering respect required to actually manage and impartially validate these highly complex dual motor systems. So I want to leave you with this final thought. We've seen the sheer level of incredible engineering it takes to protect a human driver right now. But as vehicles move toward full autonomy without a human driver there to suddenly take the wheel and pull over, how will these 60-millisecond life-saving hardware reflexes need to evolve? It's a seriously fascinating challenge for the future of functional safety. Thanks so much for joining me on this explainer, and keep learning.